You're in for a real treat. Steve Cousins is the CEO of Willow Garage, and he was a PhD student of Terry Winograd's when they were doing that digital library thing back in the 90s. His dissertation was explicitly connected to HCI, and then he was at Park for a while, then he was at IBM, and over 5 years ago, he started Willow Garage. And rather than say any more, I'll let Steve talk.
Right now. Do I magically become live? Excellent. Thanks, Paul, and thanks for having me. This is quite an honor for me to be invited to speak at BayCHI. It's been a while since I've been to a BayCHI meeting, but when I was at Park and before that when I was at Stanford, I consider this kind of my home academic community. Oops. Oh, that was bad. I just closed it instead of opening it. All right. One more time. My slides have grown. I have a lot of videos, and they've grown to like 1 gigabyte, so it's a challenge for the computer. But hopefully that works. No previews. Okay, good. So as Paul said, I started out in HCI. And when I was at IBM, I managed the user group, the user experience research group there. And then I made this sort of sharp left turn, I guess, in my career to robotics. And you might say, how'd you get to robotics? I really came to Willow Garage to run a new organization. There was this opportunity to build an organization that was researchy, going to be about 60 people. It had a mission of, it's a for-profit company, but let's do positive impact on the world first and worry about return on capital second. And you don't get funders like that very often. And I thought, what a great opportunity to build an organization, so I signed up. And this was, as Paul said, about 5.5 years ago that I joined. And at that time, there was this idea on the horizon about personal robots, that maybe we could create robots that are no longer in the factories and instead are out in the world. So I want to take you through a couple of little historical examples and then give you a little flavor of what's going on in robotics. And then at the end, we can talk maybe more informally about human-robot interaction and how that relates to human-computer interaction. We're in a little building on Willow Road. That's part of the reason we're called Willow Garage. And the garage is kind of an homage to HP and Apple and other companies that got started in garages around here. I wanted to show you this. This is a... Is this on? Can you guys make this go? Can you hear this? Yeah, no? Okay, so I'll just talk over it. But what you're missing is Johnny Carson talking. This is the Tonight Show from 1966, and here he's got Joe Engelberger, who's considered the father of industrial robotics with the Unimate robot. And there it is, making a hole-in-one, very exciting. Interesting thing about the time change, so in 1966, Johnny Carson is smoking on TV in California. Okay, so that's just how much the time has changed. This goes on. This is actually a fairly long segment. It's not so snappy like late shows now. And the next thing they do after this fine task is to have it direct the band. And the whole theme of this is, this robot's going to take your job. Not actually a good thing for the father of robotics to have said, I think, but I don't want to talk about industrial robotics beyond just giving you that little snippet. Industrial robots has been the theme in terms of robotics used in the world for the last 50 years. And I want to talk about the next 50 years, which we call personal robots. Personal robots, for me, means robots that can be around people. So if you think about an industrial robot, usually there's a big fence, there's all kinds of warning lights. You don't go near this. And if you go into a Toyota factory where you see this, 8 industrial robots descending on a car every 53 seconds to weld it together, and sparks fly and everything, and then the line moves and it does the next one. Okay, that's industrial robots. If you work for Toyota and you go through that door and into where the robot is without disabling all of the safety mechanisms and making sure that it's powered off, you're fired. Right? That's the rule because it's super dangerous. We want robots that can be around people. They have to be safer, right? And once they're around people, then all these interesting interaction questions come up. And by analogy, let me start with, you've seen these computers, if you remember. early personal computers. Early personal computers were born here at Park, right? And so I figured I had to include this part of the talk since I'm here. This computer called the Xerox Alto was considered the first personal computer in 1973. That's a little before I got into computer science. And the interesting thing about this computer is that's not the computer, right? That's the computer. And you know, it's much less powerful than this computer, right? But if you look at the time scale, in 2012 dollars, the Alto is probably a $200,000 machine, depending on how you figure out inflation over that time. That's a significant cost, right? And so I'm going to show you a robot that I'd be happy to sell you for a mere $280,000 if you do open source, a little more if you don't. And it's a research prototype, like this was, in some sense, a research computer. But I think that the PR2, the robot that I'll show you, is the precursor to personal robots, the way that this computer was the precursor to those personal computers you saw, and ultimately to the cell phone in your pocket. And of course, it was used for all kinds of different things, graphics and education. And in fact, the PR2, I don't know if I included any video today, but if you're interested, I can show you a video of it at the Tech Museum, or if you go to the San Jose Tech Museum at the beginning of December, you can actually interact with the PR2 robot, very much like the way these kids are. And we have 3-year-olds programming it, making it move. So our mission at Willow Garage is to create a new industry in personal robots. We're lucky to be able to have a mission that broad as a small company. We're about 60 people, so it's maybe a grandiose claim. What we're trying to do is somehow be a catalyst to get an industry going. And I'll tell you a little bit about how that's been going, but that's where I'm coming from. Again, the goal is impact first and return on capital second. So I want to do this, right? I want to create an industry, and I want to have it have a nice hockey stick growth curve. But of course, you know that never happens, right? Real growth curves always go like this, right? You go up, and somehow you have to end out. There's actually another way you can end up. You can just crash. But it doesn't go up forever because, for obvious reasons. And if you look at, just an aside, if you look at the semiconductor industry and other industries like that, when you actually get a growth curve that kind of approximates a hockey stick, a lot of times it looks like this. A lot of little hockey sticks, right? So TTL logic has its S-curve, and then CMOS has its S-curve, and all together you get Moore's law, right? Like right now we're looking at many cores as kind of the latest way to keep getting more processing power for the dollar. So this is an early personal robot. This is actually where we got started in personal robots. This is a robot at Stanford. That was Eric Berger, and in a minute you'll see his partner Keenan Weiberbeck. They were in Ken Salisbury's lab over at Stanford. And this is a robot that was created to be a platform on which you could develop software, okay? And this is, again, 2007, so about 5 years ago. And the idea behind this robot, let me say something about it first. You're seeing the robot doing all kinds of humanoid things, right? So it's practically ready to take over the world, right? It's actually not. I wouldn't worry too much if I were you. This robot, this is sped up. This robot was being driven by Eric in the same room. So it's teleoperated, but not only teleoperated, it's same room teleoperated, and that matters a lot, right? Because situation awareness, if you're trying to teleoperate something 2,000 miles away, is really different than if you can actually hear the crash when you knock something over, right? And so Eric was teleoperating this. This, coming up, by the way, is the world's laziest grad student in the most important task any robot can do, which is to bring you a beer. And so this robot was created actually out of plywood. I have this robot in the lobby at Willow Garage. And it was made with a laser cut plywood in order to basically prototype quickly what you could do in hardware. The robot's, again, not autonomous. So we call that the PR1. They didn't call that the PR1 at the time, but when we named the PR2, we needed to name it something. We decided to name it PR2 and back name this one PR1. And the vision here was to create a catalyst for innovation. So again, we're trying to create an industry. So the idea at the time, and the idea that Eric and Keenan and Ken Salisbury had, were that in the worst case, this was actually typical robotics PhD program, right? You're going to do some robotics work. So you're going to create a robot. You're going to somehow cobble together hardware, you're going to get motors, you're going to get a robot base that somebody else, previous grad student, has built, and you're going to figure out how to make it work again. You're going to add an arm if you can add an arm. You're going to come up with software. You're going to cobble together some open source software. You're going to write your drivers. And 4 years later, you haven't invented anything in robotics. And now it's time to start thinking about your thesis. And so you do a little bit of innovation on top of that platform, and then you graduate. And we wanted to invert that. Right? We wanted to make it so that you start with a robot that works. You start with software that works. You spend a little bit of time learning it. And then you spend most of your PhD thesis innovating, getting papers out, and making the field go faster. And we thought that this approach would actually speed things up. And so Eric and Keenan came to Willow Garage to run the personal robotics program. And the idea was, let's build 10 of these and give them away to universities around the world. So we decided we were going to build 20 of them. So we'd have 10 to play with and 10 to give away. And then if you count carefully in the front here, we gave away 11 because we couldn't decide. We had actually a lot of really, really good proposals from around the world, and we ended up giving them to Stanford and MIT and Berkeley and a lot of top places that I'm sure you've heard of. And this was pretty exciting because suddenly all these robotics labs, which used to work on their own cobbled together hardware, suddenly all had a common platform that was fairly robust. And not only this hardware, but they also had a common software platform. And the deal we made with them was, we're going to give you this robot for 2 years at no cost, and in exchange, you contribute back what you did into open source. And by the way, we're giving you, a huge investment in open source software. It was a good deal for the community. It was a good deal for Willow Garage because as a small company, when we started doing this, we were, like 12 people, and by the time we finished, we were up to about 60 people. But more importantly, we have interns from around the world. And we have a community going where lots of people are contributing to this open source code base. Let me show you a little bit about what these robots can do. This is navigation is a fundamental capability for a mobile platform, a mobile robot. Here you see it doing a little test in order to get a paper accepted. So they put some coffee cups on the floor. The robot is running completely autonomously in this, and we did a milestone at the beginning when we first had the robots moving. That was, can we go 2 pi kilometers? So pi kilometers one day, recharge, next day do pi kilometers again. We thought that would be pretty good. We actually did later a whole marathon, and this is another task that we wanted to do. How do you know that the arms work? Well, let's see if we can plug ourselves in. So the robot learned how to plug itself in. Turns out plugs are not designed to be plugged in by a robot this often. And so the robot does fine, but we often have to call in an electrician to replace the outlets. But nevertheless, it can recharge itself. We did, okay, this is interesting. So this robot's designed to be ADA compatible, right? So it goes where wheelchairs can go. So it's about a wheelchair size, and you don't want it to fall over. So it's like this big, right? And that's kind of big, right? And so if you get 10 of them in, or no, you have 9 of them in Willow Garage, they would pretty much fill this stage. They take space, right? So you have to actually think about who's going to, where are you going to park these things? And you have to plug them all in, and they all suck 15 amps when they first get plugged in. So you have to all be on their own circuits. So we end up putting in a circuit for each robot and a parking space. So there's, where it is. There's always a place for it. So with this capabilities, with navigation and with plugging in, we were able to do what we call continuous operations. And we pushed the robot last year to 140 kilometers over 2 weeks operation. Nobody touches the robot. It goes around the building. We don't engineer the environment in any way. And we just ask it, don't hit anybody, don't hit anything, right? And so it's actually pretty cool. The robot's going along, and you jump in front of it, and it stops, or it goes around you. Plans around you. If you block its way, it plans a different path, and so forth. And so it looks intelligent, right? Well, it's not intelligent. It has an algorithm that says the same thing that I tell my 16-year-olds learning to drive: don't hit anything, right? That's the rule. Sense the world, don't hit anything, and then go. And then there's algorithms on top of that for keep track of where you are and plan a path to where you want to be and then navigate. So that's pretty much what the robot does at the navigation level. We wanted to see what else we could do. Once we had this platform, this hardware and software platform, and I'll talk more about software in a minute, we wanted to see what the robot could do, and so we gave our team a challenge. You have 1 week to make the robot fetch a beer from a fridge. right? And so this is what they did. They built a web interface. If you select a Guinness from the web interface, it'll choose a Guinness and from the refrigerator and take it to you. If you choose a Bud Light, it'll ask you, do you sure you want a Bud Light? And if you say yes, it'll bring it to you. And then we actually the team added a little cup holder there so that it can hold the bottles. It makes sure to close the refrigerator securely, another good thing to teach your kids. And this is all just kind of rote programming. Once it knows where the handle is, it just goes through that entire exercise, including finding the right beer. Then uses the navigation capability to bring it to somebody, and then handoff. The handoff is actually also hard because the robot has to know when to let go. So you start talking about robot interaction, that question of when should I let go of the beer, if you let go too early, it's not good. This is the same behavior you saw in the PR1 video, but that was autonomous, although that's not robust. And here's Eitan making a mess. So we created this hardware, and I'll show you a little bit more about the hardware in a bit. We also created this software called the Robot Operating System, or ROS. And the interesting thing was, if you look at, this is a little bit old now, but 92 repositories by the end of 2010 or maybe beginning of 2011, and that's continued to grow. Those repositories each represent a place in the world, like a university typically, that is creating open source software and contributing it back. And the model that we had was, we don't want to own the open source software. We want to create this ecosystem of robotic software, and academics need to get credit for what they create. That's part of the deal in academia. So you create a repository, you put your software in your repository, and you just ask the ros.org, the community indexer, you just tell it about your site, and the indexer will go through and make it available to everybody else. And that works across our software and lots of other community software, so well over 100 repositories now. And remember I said we gave away 11 robots, right? So there's us plus 11, that makes 12. That means there's a lot more people using this, and they're not on our robots. And we did, in the end of 2010, start selling robots. We've sold probably twice as many as we've given away, which is not a lot in the scheme of things, but is a lot in terms of the number of great robotics universities in the world. But 30 is still a lot less than 100, right? So all these repositories are other robots that are running ROS. Also, if you look at packages, so we structure the software so that each individual piece of functionality is its own package. And then you put packages together into stacks, and you release stacks and version them and quality control on stacks. And that's how the ROS community works. There's well over 3,000 packages now, which is great because that's a lot of software functionality, and it's horrible because it's hard to find things, right? And so we're now adding social networking tools to help you sift through that. And it turns out that a lot of those packages are written by a graduate student who did one thing, and it's 3 other grad students in the world are interested, but most people aren't. But a lot of the packages are kind of core to running robots. Those are the packages that we've supported. Sometimes the graduate students will leave. We'll pick those things up and put them into the core and then support that. And I say we, being the ROS community, which Willow Garage is an important player in, but no longer the only player in. So let me give you an example of some of the robots that use ROS. This was our robot, the PR2 at the University of Pennsylvania, playing music. This is another robot those are the orange things, those orange arms are called KUKA lightweight robots. And this is that was an example from Munich, making pancakes. Here's robots in the University of Pennsylvania, quad rotors that are doing really cool things with ROS support. This is another arm from Stanford that's made out of plywood. Stanford does things that are not in plywood, I'll just point that out. These are PR2 dancing with a robot from Germany called the Carobot. This is a robot that's designed to go in tubes and clean out pipes. This is a car, an autonomous car that's running ROS. You can see some of the visualization tools that it was using in this example. This is a surfboard. The surfboard's not technically a robot. It's hard to know what a robot is, but that's not. But they put an accelerometer on it and then use the ROS tools to see. This is a TurtleBot. So this is basically a Roomba with a Kinect on it. And I'll show you that later a little bit more. Lego robots. This is a PR2 again, and a robot called Ellie from Georgia Tech. So this is one of those home-built robots, but with a commercial arm designed for research labs. These are servo bots. A lot of times you see little tiny robots made out of airplane servos. There's a lot of robots in that category. and they can run ROS. So you get an idea. I need to update this video, because there's a lot more robots, and some of them are really interesting. Like somebody built an artificial rat with whiskers that runs ROS, and I thought that had to be on here. So Willow Garage as a company, we started 5 years ago, and our idea was, let's be a catalyst to create this new industry. And as I kind of indicated, ROS has been really successful, the robot operating system. The PR2 has been pretty successful. Where we want to go now in the next 5 years is, how do we get robots in use? How do we get robots out there among people doing more things? And obviously cost is one big issue, but and we're working on that, and lots of other people are. But I want to give you a little bit more sense about robots and where they might be useful, and what we can do today, because there's a lot of misperceptions about robots. You know, I hear a lot, and I get asked a lot about our coming robot overlords. I don't really lose any sleep over that, because I get to see robots in the world doing things. But let me show you the probably most compelling example that we've found. This is a man named Henry Evans, who about 10 years ago, he was a CIO in a Silicon Valley company, had a brainstem stroke, and suddenly was quadriplegic, right? And it's a tragic thing. He's able to now move his head, he can click a mouse with his left thumb, but that's pretty much the motion that he has. Henry can speak, he can write. If you actually look on the web for him, he's written a whole description of what it's like to be trapped inside this body. But he saw this CNN clip with a PR2, and he said, you know what, I can use that robot to be my external body, to replace my worthless body, as he puts it, which was really exciting. And so we thought he was going to do things like you just saw with, you know, picking up things. He's actually controlling the robot in this scene. He's controlling the robot from this screen using a web interface and making the robot do things. The thing he wanted to do first was he turned the robot on himself. He brings the arm right up to his face, and we were like holding the run stop, like, what are you going to do? He wanted to scratch an itch. Yeah, exactly right. And then he wanted to shave himself. We actually did some science here. We tested how hard he pushes with using a force torque sensor, and also how hard his wife pushes when she's shaving. It turns out he pushes 10 times harder than she does, which may explain why he wants to shave himself. He's a delightful man, and he can't speak. So he basically literally is trapped in his body. Here he's using a robot to go to another room. So remember in the PR1, it was in the same room. This is him now using a much less sophisticated user interface, just web clicking, to another room to put these objects in a drawer. One of the coolest things that he's been able to do is, in his own home, drive the robot from one end to the other, open a drawer, get out a towel, come back, and use it to wipe his face. Right? Which is, think about, you know, when you're in the situation, if you can imagine being in that situation, the amount of dignity that he can gain by having control over that kind of operation himself. It's really enormous. And so I've been really, really excited about this project. He named it Robots for Humanity. And it's been a collaboration between us and Georgia Tech, and also the Washington University, and Bill Smart there is now at Oregon State University. So this is at the other end of the cost spectrum. The PR2 is not in Henry's home yet. This is a TurtleBot, and as I mentioned, it's basically a part of a game machine, the Connect, and the Create is basically a Roomba without the vacuum cleaner, which is really the same thing. I shouldn't say that. And it has a netbook in it. And the TurtleBot is able to you know, because it's got the Connect, it's able to do a little bit of skeleton trapping. The cool thing is this is about a $1,500 platform. You can buy it from a company in Canada, or you could actually build it less expensively than that if you want. The hardware design is open source, and the software is all open source. And so people are using this to teach robotics in classes, at least basic navigation things. And I want to tell you this story about a robot that we thought of it as a robot at first, and I think it's actually kind of pushing outside the category. This is what we would call a remote presence device. And the man who's standing there, his name is Kurt Myers, we were trying to build the PR2. And one of the things about the PR2 is that you have, I don't know if you guys know much about robotics, but you have motors. And I always thought, oh, you have motors, you attach a battery, the motor goes, which is true for some motors. But usually you want a motor controller, right? You want to control how fast it goes, what kind of torque there is. And there's actually substantial electronics. And the better the motor and the more sophisticated motor controller you want. And if you want to build a robot, you could do what industrial robotics do, which is they have a box about this big, and then you have the robot arm, right? And this is some old PLC, programmable logic controller kind of thing. A bunch of cards in there. It looks like probably the same kind of electronics that was inside the Xerox Alto that I showed. And it's running this big robot arm. But if you're doing a mobile robot, you really don't want that big piece of hardware. And so the ideal was to design a very small motor controller board. And it's a challenging electrical engineering problem. So we outsourced it to some company. We didn't have anybody besides Kurt who could work on it, and he wasn't ready to do it himself. And they failed. Right? They couldn't build the board that we wanted. We couldn't find anybody who could build it. And finally, Kurt said, I know this guy in Indiana. He'll do it. Right? And so we called up, his name is Dallas, and he's the one on the screen there. We called up Dallas, and we said, Dallas, we want, can you help us build this motor control board? And he said, sure. So he was a consultant for a while, and then we hired him as an employee. And so his day-to-day operation was working on this board, and he was working from Indiana in Menlo Park. And I couldn't figure out why he wanted to do that until I asked him, and finally he said, my house is a lot bigger than yours, Steve, which is true, but it snows there. So I grew up in Chicago. I'm staying here. Anyway, Dallas wants to live in Indiana, 2,000 miles away, and you know what this experience is like if you're the person calling into a meeting where everybody else is sitting around the table. It's not actually very good for the remote participant. So he wanted to try Skype. That's going to be better. So he put us, can I requisition a laptop? Okay, we get you a laptop. And I only know that Dallas exists because I get this request for the laptop and I have to pay taxes in Indiana, right? But he's out there working, and the Skype was okay, but the camera's not very good, and he doesn't have very much field of view. He can't look around. He can't see the screen. Can I get a better camera for it? Okay, you can get a better camera for it. Well, so they go off and they built this cart, just like they bought a cart and they put the computer on it, they put a screen on it, they put a nice camera on it, a nice microphone, uninterruptible power supply so that they could have it in the lab, and then they could unplug it while it goes beep, 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 and push it into the conference room and plug it back in, and so he can kind of be there. And they're like, wait a minute. We're a robotics company. We can do better than this. And furthermore, we've got leftover casters from a previous design revision of the PR2. So let's build this frame. Let's put a caster from the other robot we're building. Let's put a car battery at the bottom to power it. Let's put all the other pieces we had back on it, the computer and the screen and everything. And suddenly you have this device that Dallas and again, using the robot operating system that we've already worked on, he can drive it from Indiana around the building at Willow Garage. And suddenly the whole relationship between Dallas and this company he works for, our company, is changed. Right? Before, he doesn't exist. Most people don't even know he exists, and he's only a voice or a face on a screen. Suddenly, he's driving down the hallway, right? And so I'm walking down the hall, and I go, hey, Dallas. He goes, hey, Steve. We walk by like a normal interaction. He drives to the cafeteria at lunchtime. He doesn't eat, right? But he can come and join those conversations. If he wants to go to a seminar, if he sees a seminar happening, he doesn't have to say, can somebody set up the videotape and stream it or whatever. He just goes. He goes where he wants to go. If he wants to catch you in your meeting, he goes and catches you in your meeting. It was really interesting and really life-changing. And I'll take credit for one thing here, which is while we were trying to get this PR2 robot done, we were behind schedule, we got to get this thing out the door, this project came along and distracted the whole EE team, right? And so my claim to fame here is I didn't kill this project, right? I said, okay, go ahead, just kind of get your other stuff done, can you? And so at the end of the day, you have Dallas driving down the hall like this, and this was the first generation of this contraption. The next thing that happened was that we created this a bunch of copies of that, cleaned up a little bit. So we did an engineering revision. We made about 27 of them, and we sent them out to different Bay Area companies to try as trials. And we knew we were onto something when they wouldn't give them back, right? We had to kind of reclaim them. And so at that point, and also we got a little bit of notoriety. So as a side note, I don't know if you've seen The Big Bang Theory and the Sheldon bot, but that was this robot. In that case, he called it Sheldon bot, so I call it a robot. But we now think of this as really a new category. It's not a robot in the sense of, it's a worker, it's a slave, the way that robots are historically. It's not the way that Joe Engelberger talked about on The Tonight Show. It's something different. It's something that allows you to be at a remote location. And so we spun out this company, Suitable Technologies, and I'll encourage you to go look at suitabletech.com at the video there, because it's actually very compelling. They've just started shipping products. I think we have the first 4. And they created this thing called the Beam, which basically does this and solves some of the early prototype technical problems that we had with the ones that we put in the field. So it's actually really, really exciting. And is a new way. So I think of this as kind of part of this growing in industry. I always forget to unanimate this slide. So part of the question people ask me a lot is, well, what's your business model? How does this work, right? And one of the things that we're doing, in addition to trying to create the next robot that that's going to be more widely used than the PR2, is to create spin-off companies in various areas. And so we've created in the last 2 years 7 different spin-off companies, Suitable Technologies being the first one and the first one to release a product. But there's a company called Redwood Robotics that we've worked on as a joint venture with Mecha Robotics in San Francisco and SRI, which is doing a low-cost arm, because we know from the PR2 experience that the arm is the most expensive part of a personal robot. We created a company called IPI, Industrial Perception Incorporated. IPI is taking some of the low-hanging fruit from the computer vision field that's been worked on over the last. Computer vision has been going on and on in sort of a continually incrementally improving area. But they take some of the low-hanging fruit and applying that to industrial situations where they can provide the vision component for an industrial robot that's going to try to grab things. Most industrial robots today are blind, right? They're basically doing rote work, doing the same thing over and over again. If you can start to add sensors, cameras in particular, or 3D sensors like the Kinect or other 3D sensors, suddenly you can automate more of the work in factories, and that's usually that's pretty boring, redundant work. And then the third one, or the fourth one on the commercial spin-offs, is called high DOF. DOF stands for degrees of freedom, which is the way you describe how flexible a robot is. So high DOF is a clever robotics pun. And this is a consulting company that's actually out there. We created this robot operating system. It's open, but this is maybe the beginning of a red hat for robotics, or consulting at least. And then on the other side, down at the bottom, are nonprofits that we've spun out. So we create all this open source software, and we're trying to get an industry going. And one of the things that the other robotics companies say is, well, why should we use your software, right? You guys, what if you change your mind? And we're like, well, we licensed it under a BSD license, so it's available for commercial, non-commercial. You can always fork it and take it. And they don't get that, right? Especially robotics companies. They're a little bit, remember, they're still using PLC controllers. And so we created the Open Source Robotics Foundation with we created it as a spin-off, and then it got a big grant from DARPA to work on essentially open source robotic simulation. And so that's kind of a really nice incubator. We created the Point Cloud Library because a lot of companies are interested in 3D navigation. So Trimble, for example, is a company that used to make GPSs but now makes now reasons about the 3D world. And so they're interested also in supporting it. So we create nonprofits that handle this open source software so that it's out there in the open. And then OpenCV, of course, is probably the most widely used computer vision library in the world. Came out of Intel, and we've been supporting it, and now we have a foundation for it. So let me go back to this question, because there's really two ways to look at robots. I want to look at what we can do autonomously, and then remind you that the Henry Evans, the Robots for Humanity work, is really not autonomous, right? It's human in the loop. And I think that the world of robots coming is going to be both autonomous and remotely operated. And there's a lot in the middle, right? So when Henry went to shave himself, the first time he did it, we were using what's called a Cartesian controller, right? You tell the arm, go forward, 3 inches, go right an inch, go, turn 90 degrees or whatever, right? And he's trying to do this. So in the robot's perspective, right, he's sitting here, and he's trying to get the robot to do this with its arm. And by the way, in order to tell the robot what to do, he's having to move his head. So it's literally a moving target, right? And it was challenging. And it turns out if you use a little bit of autonomy and a little bit of intelligence, you can model this problem mathematically. And smart robotics graduate students will look at this problem and say, oh, his head's kind of an ovoid, so let me detect where the head is. And since I know where the head is in 3D, because I have a 3D sensor, I have a Kinect, he just clicks on his face. Just, on the screen, he just clicks on his cheek. And then the robot says, oh, I can plan a motion to get the arm right there, 1 centimeter off. And then he can do this, right, if he wants to shave, right? And that just makes the problem a lot easier. So it's like you look at the problem, you provide some simple, it's still mathematical, right? Cartesian is a mathematical approach. But then you look at it and go, oh, I can apply a little bit better math and figure out the normal, surface normal to a point in the world, and suddenly I can do better. What else can we do autonomously? This is probably the most popular PR2 video. This is work that was done at Berkeley, actually done at Willow Garage by Berkeley students before Berkeley had a PR2. And this is folding towels. And this has had some enormous number of hits on YouTube. And I'll show you why. Right here. If you're going to do that. And I think that's just like sells the whole YouTube world. It's just so cool. Now, I don't want you to go away thinking that robots can do your laundry tomorrow, right? So this is a robot that retails for $400,000, and it was taking 25 minutes per towel, which is only good if you talk to a reporter who inverts numbers and says it's 25 towels per minute. Then it's okay, right? But 25 minutes per towel is not actually a good time. To their credit, they can now do this in 3 minutes per towel, which is 8 times speed up, but still kind of slow compared to how you fold towels, I guess. But it's a cool application. And the reason this is cool from a robotics point of view is, again, robotics is a lot about mathematics and modeling the world. And grad students in robotics are really good at that. This is a challenging problem. There's no good model for that towel, right? It's just it's soft and it's just a blob. And so they use a theorem, right? There's actually a towel folding theorem. I'm going a little bit off from HCI, but it's kind of fun. If you grab a towel and you hold it up and you shake it, right? The lowest point is guaranteed to be a corner. If you grab that corner, you hold it up, shake it, that's the opposite corner. And so if you do this, you actually get 2 opposite corners, and it's going to, if you put it on a table like that, if you have a big enough wingspan, right, you get this kind of zigzag. And the whole problem is figuring out which of those 2 triangles is on top. Because once you got 2 adjacent corners, you can follow that algorithm and smooth it out and everything. And folding's easy once you get it to that point. So the 25 minutes per towel, most of the time was it grabs this thing, shakes it, and it holds it, tries to find that bottom point, and then shakes it again. And they do this twisting thing. And they're just trying to find the other corner using image processing that's nearby. And that's actually pretty hard. Even if you wanted to do that, it's not a trivial way to do it. There's probably better ways to figure it out. But there are towel folding robots in the world, but the way they work is humans feed them, right? They find the corners and they put the 2 corners in, and then the robot does the rest. And in those, like in big hotels, that's what happens really fast. Okay, that's the end of that digression. Here's another really fun. This was another hackathon, another 1-week challenge to the team. Can you make the robot play pool in 1 week? What you're seeing, so there's the robot. We added a little stick to it. We added a little hinge mechanism so that the arms aren't really fast enough. They're not designed to move fast because they want them to be safe around people. And so this hinge mechanism lets you use the wrist to get some torque and get some speed on the stick. The other cool thing about this, when they looked at the problem, they said, well, what we're going to do is we're going to use this open source pool physics simulator that we found on the net, right? And it tells you, it's this thing on the left over here. If you give that simulator a model of the table, so where are all the balls, where are the pockets, it'll then do this, right? It'll sort of do a search through all possible places you could put the cue ball and tell you the shot that you should take, right? Now that's a first shot at it that didn't work. Here you see balls going in, and by the end of the week, by the end of 1 week, we had it doing shots like this and nice angle shots like that, and we said that's pretty darn good, right? So this is we're going from a place where, again, it used to take a grad student 4 years to kind of get a robot up and working, to where suddenly in a week, a team of 8 people can, they're trained people, but still, a team of 8 trained people can do a brand new task from scratch, and we were pretty excited about that. So this is actually also really cool. This is a grad student from Georgia Tech, and he's got a robot. This has just got it standing there, and he's moving a glass from one point to the other. And it's kind of a cool thing to be able to move back and forth, but it's not rocket science until you realize he's moving it kind of fast, and that one's full of water, right? This is one where he doesn't use his algorithm, right? So what he's doing is tilting very subtly as you move. So again, the robotics grad student approach to a problem is to say, let me think about this mathematically. When I start to move this way, there's a force on the object that's the other way. If I tilt a certain amount, I can counter that force dynamically. You do that mathematical modeling, and at that point, you can just do this thing all day long. And it's really cool, right? As long as the robot is sort of fast enough and precise enough and responsive enough, you can just hold something on a slippery surface without spilling it or take a glass full of water. So when I talk to students about robotics, I usually point out that there's a lot of cool math. You learn math, and you're going to get some pretty good value out of this. Let me just give you one example of how does it work. This is sort of what the robot's seeing inside as it tries to pick up an object. If you put this bottle on a table and have the robot pick it up, we're pretty proud of that at this point. It's building those lines that you're seeing. That's its tilt laser. So it's building a 3D map of what's on a table in front of it, segmenting the objects from the table, and then identifying those objects. And then once you have an object identified, you have to grasp it. So what you see jumping around in the front there is a simulated gripper trying all different grasps in order to figure out the best way to grab an object, because you don't want to necessarily grab it this way, right? This may be a better grasp. Once you have the object you picked up, you want to make sure that as you move, you don't hit something. So here is picking up an object and moving it without hitting the other objects on the table. That requires a planner. It turns out that if you're a computer scientist, that planner is NP complete. Or that planning problem is NP complete, and so you have to do simulations and estimations, stochastic simulations, to try to figure out where you want to move. And then sometimes there's sensor error, so you don't know exactly where the gripper is. And so, excuse me, if you misgrasp, in this case they move the object on purpose, the robot will actually feel where it missed the grasp and move its gripper to the right place. So here's a complete pick and place action, right? Basically pick something up, make sure you got a good grasp of it, and then move it back. You'll notice that the robot sped up 4 times. To watch this in real time is a little bit painful, right? Robots aren't that fast. Robots that are sensing their environment and reasoning about them and acting on it are not that fast today. There's a lot of compute power. The PR2 has 2 basically Mac Pros in its base, has i7 processors, 8 cores in each computer, so 16 total cores, 48 gigabytes of total RAM, a couple terabytes of disk. It's a pretty beefy system inside there, and it's running like crazy to try to make these algorithms work. So there's a lot of room before the robot overlords get here. We did something called the Sushi Challenge, and the Sushi Challenge, this is just a sushi restaurant in London, here's an example of the robot trying to pick something up off of a moving table. And again, this is one of these, we thought this was going to be hard. We thought that picking up an object from the moving table was a task that was hard, because usually you watch a robot in action and it sits, thinks, and finally starts to move and grab something. Well, if the world's moving, what are you going to do? That problem, and I cut the video badly because you didn't get to see it actually grab it. But in this case, what happens again, the smart mathematically oriented grad students say, oh, we can model the motion. It's just one more degree of way we represent the world. So it's easy, so we model it mathematically, and then we watch for a while, we have our model, we just grab and pick it up. For a while still means like 30 seconds to a minute, so it's kind of still slow to watch, but things are getting faster. And then there's this area between the demos and total autonomy. This is us doing this sushi challenge. The sushi challenge is to clear this table in the front, move all the dirty dishes over to the dirty dishes area, which is in the corner there, go to the clean dishes area, get new plates, set the table, and then go to the rotating table and pick something up, right? And so the first time we tried this with human in loop. So we have a teleoperator using a web interface and trying to do this task. And you can see, I can tell by watching this that that's a person doing this. It's not, the robot doesn't just grab it. It's actually like moving things, moving it to the edge of the table to make its job easier. Robots don't plan that way. Picking up the chopsticks ends up being a challenging part. You have to get the gripper just right. This is something that actually the robot would do autonomously, would probably do better than a person, figuring out how to exactly get the gripper there. And setting the table ends up being reasonable, although the challenge here is not what we expected. The challenge here is you have stacks of plates, and grabbing just one plate is really hard for these little parallel jaw grippers, right? If you had a full functional hand, like a human hand, and a lot of training, you could teach it how to do what we do, right? We grab it, we kind of pull it with our thumb, we can take the object out. But that's hard to program, and not only that, it's really hard to build that hand in such a way that it's robust. So there are some robotic hands out there, fully featured, but they don't tend to last that long in practice if you're going to work with them. So these parallel jawed grippers tend to be like the simplest thing ends up being the best thing, the easiest thing to maintain. Here you see it actually taking the extra plate that it grabbed back. Now, the last part that I want, he's going to struggle with picking up this. You know, I set up this problem and I said, here, try to solve this, and of course, you know, it's never so easy. So then the roboticists try to simplify it, but this roboticist was actually trying to be brave and do it all exactly as I set it up. And it turns out that those chopsticks in the little bin were really hard for the robot. And the operator basically can just see what you're seeing in the upper corner there. He doesn't get to see the third-person view. So he gets the table set and try to make it all nice. And then he's going to go try to pick up things off the rotating table. Now again, a robot doing that, not so hard. A human doing that through a robot. Actually, human doing it's not so hard. Human doing it through a robot, that's hard. And I fast forward a little bit and see that. So those ones he was able to grab relatively straightforward. I watch him try to get this plate. The reason is that the gripper doesn't just snap closed, right? The gripper goes, and things moving fast, right? So he just can't get it. And finally, I mean, he's got a lot of patience. It took him 40 minutes to do this task. This is video sped up. If I asked you to do this task, it would take you about a minute and a half, right? So, so we got a ways to go, even on the teleop side. We were able, simplifying the problem a little bit, basically doing objects that were easier for the computer to for the robot to recognize. We were able last April at the big robotics conference in Minneapolis to do this entire task autonomously in 30 minutes. So that's not bad. It's not good, but it's not bad, right? It's sort of coming in the right direction. And it was actually kind of a tour de force for autonomy. So I wanted to give you a sense of where we are in the world. Let me show you, this is the other thing that's happened with the robot operating system. That's one of those big controllers I was mentioning. This is an industrial robot arm here, and one of the big controllers next to it. But now they're running ROS, the robot operating system, on these industrial robots, which is a big breakthrough in industrial robots, because suddenly it makes it much easier to program the robot. I look at this video, and you probably look at it too, and go, so what did you do? You got it to move from up here to down there, and that was hard? And the answer is, yeah, it was actually hard. Before, it was people would take a long time making sure you didn't crash into the side of the controller. And now with the software, can basically do that planning and do it automatically. And if you're in industrial robotics, apparently you get excited about this. So let me end with one last slide, kind of my predictions on where robotics is going, and then we can stop and maybe just have a discussion about the human-robot interaction aspects. We've already had a little incursion into personal robots, right? Roombas are arguably robots. They move around in the world and they do something. And And there's like 7 or 8 million of them out there, right? And they have interesting phenomenon around Roombas. They not only exist in the world to vacuum, but people name them. Something like 40 or 50% of the people who have Roombas name them, which is shocking. Shouldn't be shocking, I guess, but that's so it is. There's a wave coming, which is these remote presence devices that I showed you. And I think that's going to be really exciting. And again, the reason is, if you think about somebody who has to travel, like I used to work for IBM and I had to go to New York about 6 or 7 times a year. And every one of those trips cost me, or cost the company out of my travel budget, $1,500 to $2,000, right? So you do the math and you say, gee, I'm going, traveling 7 times a year, it's going to cost me, $10,000, $15,000. If 2 people are doing that, suddenly I could just buy one of these remote presence devices and have it there. And if that could reduce, let's say I could only go twice a year instead of having to go 7 times a year and go with the robot instead, suddenly that thing just pays for itself out of my travel budget. Whenever you have a business case where you can say where the money's coming from and who wants it and why, I think you have a pretty good business case. The next step after that is what we call act there. And think of this as what the Robots for Humanity was showing you, right? This is Henry being able to act in the other room, or even be able to act on his own body in the same room, but be able to do remote manipulation. One of the cool things, I showed you Henry shaving himself using the robot. He's also able to shave other people. So one of the cool demos, or tour de force demos, I think, for the project was when he shaved Charlie Kemp, who's a professor at Georgia Tech on the project. He shaved, Charlie was in Atlanta, Henry was in Palo Alto, and Henry shaved Charlie. So Charlie could say, my barber is a quadriplegic who lives on the other coast. Right? This is pretty cool. And finally, after those phases, I think you get to automation, right? You start to get to Rosie from the Jetsons, but without the attitude. Maybe the attitude comes later. I don't want to predict that. So with that, let me stop and maybe just have a brief informal discussion.
I think that the best example of the computer-human interface was the touch your face rather than, yeah, I mean, you didn't point that out, but that was clearly a tremendous advance.
Yeah, I mean, the interesting thing about human-robot interaction is that it's not quite like HCI, right? HCI, there's me, and there's my computer, and you can think, okay, the keyboard design is kind of ergonomics, but how the screen looks, we think of that as HCI, or interaction design. With the robot, you have the person who might be driving the robot or telling it what to do, and so there's the interaction between them and the system, which typically is remote and often like a computer interaction. And then you have the local who's interacting with the robot, who, depending on whether there's a person operating the robot or it's autonomous, that interaction is different. And speech is a pretty important potential interface there, but so is gesture, so is touch. You could put a screen on the robot, although if you think about it, it's a little bit weird if you have to touch, especially if I'm doing telepresence, right, and the controls are here. It's like, oh, you're poking me in the chest, right? We actually had an interesting example of, I think maybe one of the first computer assaults using the remote presence robot. So somebody who was a pilot, so they were remote, they were driving the robot, they annoyed a local. So the local hit the run stop, turned the power off. Right? I mean, you don't do that to somebody who's in your space, right? I mean, you can't just your wife's yelling at you and you say, sorry, honey, right? I mean, it's not considered good form.
I have another question. This issue of how long it takes to get things done. I mean, I remember the time when machines were very, very slow, and machine efficiency was a really big deal, and it still is in certain areas. Do you think that that's an aspect of it? I mean, is that an approach that should be taken to make the operating system and the programs and so on more machine efficient? Well,
of course, you have to start with a demo that runs at some speed, right? So the towel folding is really cool, even if it's not practical today. But it's, and you will see speed ups over time, right? And I think in any case, yeah, you're going to see the machines getting faster. I don't know that machines are going to get a lot faster than people for a long time. I mean, you can definitely make robot arms that move faster than you can see them go, doing motions. And you can do high-speed cameras, and robots can do amazing things on the very expensive scale. But if you think about the amount of computation that's used for that, the amount of watts that are used, humans are amazingly efficient, power efficient, and have enormous dexterity. And so it's not clear that robots replacing human labor is, I mean, of course, machines regularly replace labor when you can automate the task, but general purpose, replacing everything that you do, I don't think it's going to happen for a long time. But special purpose things, once you identify a task like delivering room service in a hotel, that's something that's automatable up to the point where, depending on the hotel, it may or may not be acceptable for a robot to be giving you this as opposed to a person, right? It depends on your attitude toward other people, workers. Some people actually would prefer the automated solution. Some people would absolutely hate it, right? And so that's very much a cultural thing. Yeah.
Hi. This is a little bit of a futuristic question, but I'm wondering if there's any research going on with integrating biological systems with, with robotics, and I'm thinking both in terms of the computational or decision-making ability, and the just the manipulative ability, because obviously a fly has a lot of intelligence and very quick response times, just flying around the room making decisions. But we have these complicated, heavy machines trying to do similar things. So.
Yeah, I think that there's a lot. I mean, you asked about robots augmenting people, or robotic technologies augmenting people, and you can actually see a lot of that. There's exoskeletons, which is a really nice example of that. So if you don't have, if your knees can't support you anymore, but you add an exoskeleton, suddenly you can walk again. There's the Google glasses, right? So suddenly you're augmenting your intelligence with, external, sort of augmented reality, which I think has been talked about in the HCI community for a long time, and suddenly is starting to get there. It's not maybe necessarily a robotic technology, but it's the merging of technology, digital technology and analog technology with people and their bodies. We have a lot of examples of, you're starting to see examples of robot arms on vets, right? Somebody who's got an amputee, but there's nerve endings there, and the nerve endings are retrained to control a robot arm so that that person can, I've seen an example of picking up a grape and eating it, right? That's pretty cool. It's not cheap right now, and there's questions about, how's that person who doesn't have arms going to get that thing strapped on? But once you strap it on, it does give you a capability that you didn't have before. And so I think in general, robots for people with disabilities is a really, really important area. It's not, as a market, it's not a huge market. Thank God, I guess. But it is a really important area. And it's going to generalize to elder care, right? So as you lose functions as you get older, robots can help you regain some of those functions. And at some point, it comes down to independence, right? We all want to be independent as long as we can. And if the robots can help you do that, that's really powerful. That's the directions that we're looking. Yes?
So just to build on that, there's a lot of places where there's natural interfaces. For example, for the Da Vinci robot, which they use for doing operations, and a lot of the video or the laparoscopic ones, you have real operations. And you could even have walking by doing something which is equivalent to the Segway. You lean forward and you go forward, or brain waves. So where do you see that sort of thing going?
Well, all those things are happening, right? I mean, you can use the robotic technology to magnify your motions. So you see somebody like soldiers typically doing this, or actually this is what construction workers do, right? They're running a big digger, right? They're essentially magnifying their own actions. And you can work on a micro scale. That's what the Da Vinci does. Lets me do surgery with the little tiny end effectors. And there's beginning to be able to understand how brain waves work and model that and get commands. It comes down to, what are your abilities and what do you need, right? And we're in this, robotics is a really exciting area in terms of designing these interactions between people and doing what Mark Stefik would call the dance of the necessary and the possible, right? What can you do with robots? It seems enormous, and when you actually dig in, it's like some of the things you think would be really easy. Robots will do this really fast. Fold the towels like that. Well, that's hard, right? But some things robots can do really easily. Like they're all telepathic. Like, what do you mean? Well, they have Wi-Fi built in, right? So they can think to each other. We can't do that, right? And so you have this interesting dichotomy. Robots are really bad at perception. That's why 2 of our spin-outs are about open source perception software, because that's a really hard problem. Meanwhile, people are really good at perception. You can give somebody an image and say, where's the green ball? And they just click and go, and you do mechanical Turk, and that's a much faster way to solve that robotics problem sometimes than trying to write an algorithm to do it. And so, yeah, it's an interesting dichotomy of expertise. So far, the robots that we've built have been research robots, and the people who have them have done all kinds of things. So people have done brain-machine interface to try to control a PR2. They've done all kinds of different interfaces, actually. They've had one robot controlling another, so the robot feels force on its arm, and then it uses that to move the PR2's arm, right? So you can actually grab a robot arm and control the other robot that way. So as a research platform, we're doing all those things. At Willow Garage, we don't do a lot of BMI or brain-machine interface kind of work.
All right, question for you. Is this on? Yeah. Okay, excellent. There it goes. I've seeing a lot of videos online of sort of entertainment-based robots coming out of Japan that can have very fine motor articulation and seem to be more oriented towards, I guess, recreating the human experience and being more relatable and not really having utilitarian function, more like the stuff you're doing. So in the grand scheme of where robotics are going with these different cultural influences that sort of determine culturally what we want out of our robots next, how do you see that changing based on the cultural backgrounds of what we're doing versus places in Asia or other parts around the world?
That's a good question. I think as you point out, different cultures think about these things differently. The Japanese tend to be particularly robot-friendly as a culture, and they have a particular need for robots. One of the questions we have in this country, and I get it all the time, roboticists in the U.S. shy away from questions, is that robot going to take my job? Because we've had, for the last few years, a little bit higher than normal unemployment rate, and people are sensitive about that. And so, oh my God, these robots are going to come in, it's going to be terrible. And we're all going to go the way of the buggy whip drivers, right? In Japan, they have the opposite problem. They have an aging population. They have not enough workers to take care of them. A little bit xenophobic. They don't want to bring Filipino workers in to care for their elderly. And so they've, on the record, said, look, we want to build robots because we'd rather have robots taking care of us when we get older. And so they're more open to it. And the cultural differences are there. I mean, there's a lot of great anime robots that have come out over the last 50 years, and that's influenced the culture. And in the U.S., we had Wonder Woman, I guess.
I was left wondering what the initial few apps are that we're going to see. How are ordinary people going to start using robots? And I was wondering, is a self-driving car a robot? And is there some example of a sort of a halfway purpose-built device that people will have that'll make a particular task easier for them? I mean, what kinds of things might we see coming up in the short term?
Well, I mean, we already have a lot of, depending on how you define robots, right? We have microwaves, we have washing machines, we have technology in the house that has motors in it. If you think of that as a robot, sensors and motors and even processors, right? I would call the self-driving car a robot. I have a pretty broad definition of robot for myself. And the self-driving car is really exciting. We started out Willow Garage with a project in that area, decided that we didn't want to spend the resources to hire the lawyers to get the laws changed to allow those cars on the road. I'm really glad Google is doing that work. And Google hired I don't know if you know this, the winner of the 2005 DARPA Grand Challenge, Sebastian Thrun, and the winner of the 2007 Urban Challenge, Chris Urmson from CMU, and they're both working on this autonomous car. They've actually put together an all-star team, and I got to ride in the car. It's actually pretty good. Less scary than my 16-year-old. And so I think those are coming, and I think there's actually a really good reason for it. Sebastian makes a really good case that we lose 45,000 people a year in car accidents on the roads. A lot of those involve alcohol, and certainly if you could have a breathalyzer that says you could drive your car when you want to drive it, but if you're drunk, your car's driving itself. That would actually be a much better proposition than you trying to drive home drunk, because the cars are actually reasonably. I think they're going to be reasonably safe. I think the technology is coming along. So that's exciting. That works, by the way, in the completely autonomous case because you can model that problem really easily, right? The model is what I said for our navigation, what you tell your kids, don't hit anything, right? That's the whole rule, right? It's a little bit more subtle than that because you have to detect red lights and things. The first versions were just stay on the road and don't hit anything. And they got through that, and now they're working on the more subtle things, like what's going to happen when that pedestrian's standing there and stuff. But those are still just detect an object, recognize that it's a person or a tree, and predict what it might do and behave and proceed accordingly. So I think, autonomous cars are coming and are going to be really good for society.
And other simple applications that might come in soon?
So, remote presence is the next one, right? I think, this ability to travel on a business side, but I think that'll extend into, I'd love to have a remote presence device at my mother's house, right, as she ages. Because if I could Skype with her now, right? But if she doesn't answer Skype or she's having trouble with her computer, I suddenly don't have that contact. And so it's nice to be able to think about not only Skyping that direction, but maybe the other direction, right? Maybe she wants to be able to visit kids as somebody becomes less mobile as they get older, they may want to be able to get out, and at least getting out through a camera that you can control is better than not getting out at all or just watching television, which is a camera somebody else controls. So I think that's the second big one. And I think there's going to be a lot of special purpose kind of applications. And I can't even tell you what those are yet. We're looking hard for the spreadsheet equivalent, right? When we sort of have that PC analogy, what's the spreadsheet for personal robots? And I think we don't know that yet.
Okay, I've got a question regarding the size. I mean, the size of that robot was fairly large.
Right.
What kind of efforts are being done to reduce the size and make it a little more, a little easier to maneuver?
So there's a lot of efforts, and if you look at I can walk on a probably a 6-inch plank, right? People can walk on a balance beam, so we can get through pretty narrow spaces, and our environments have narrow spaces. That robot was designed to be statically stable, right? I'm not statically stable, right? If I go to sleep, I fall down, right? But the robot is statically stable, and it needs to get up to a certain height. So to be statically stable and get to a certain height, you have to have a lot of weight down low, and the bigger footprint you have, the less likely is you're going to tip over. So that was the design criteria for that first generation robot. As we go forward, we know how to do dynamically stable. There's, you've seen the Segway, right? Segway is dynamically stable, so it stays upright this way. If you're going on a Segway and you hit this wheel on a wall, you're going to fall, right? It's not used to that. But normally, a Segway stays upright pretty well. And there's a robot out of Carnegie Mellon called the Ballbot that's like a mouse wheel on the bottom. It's just balancing on a ball. So one approach to we have to get tall, right? Because we're tall, so we reach up into cabinets. So the robot, if it wants to work in our environments, has to be tall. We also have a small footprint, which means it needs to have a small footprint. So ultimately, you probably need some kind of dynamic stabilization. That said, we're pretty good in robotics at math, right? We can figure out when something's going to fall over. Mechanical engineers know how to do this stuff. And so we are shrinking the base as much as possible, and other companies are as well. And we can get to a size that's reasonable to be around. It won't be as dexterous and dancing as we are.
Yeah, I was just thinking something like that counterbalances, that when it senses that the weight's like the arm is moving out, it counterbalances it underneath that.
Yeah, I mean, you can, again, once you state the problem,
Right.
Then clever people can solve it. But the cost in robots matters, because size matters and cost matters and weight matters. And the cost is going to go with the number of motors. So when you try to do, this something where you can counterbalance, you've just basically doubled, you have 2 arms now.
Right.
And if you want to do 2 arms forward, what we do is we have a waist, right? And so do all the Japanese robots, by the way, right? But we didn't do that in the PR2. And at some point, that waist actually gives you some nice workspace, because otherwise you're sitting back like this and saying, well, what can I reach, right? And if you have a stiff back, it's actually hard to reach very far. Whereas if you can just bend a little bit, or what we do, we kind of turn our shoulders. We have a lot of degrees of freedom going on and a lot of dexterity. But as I said, as I've been in this job, I have a lot of respect for the human body. Yes.
So what happens if 2 of those telepresence devices meet in a hallway?
The people who are driving them talk. Actually, if you go to suitabletech.com, they have that exact example. And we actually had this come up where there's 2 or 3 people talking that way. It seems odd, right? But it actually works, and you're situated in an interesting way. It's a little bit messes with your mind, because you're here, but you're driving something there. So you've got to be thinking in both spaces at once. I think it would be really hard if you were walking and trying to drive a telepresence robot at the same time, because you'd really be in 2 spaces.
So you mentioned that there's folks working on dynamically stable platforms that use a ball at the bottom. It seems to me that's another area that the Jetsons predicted, because Rosie the robot had, if I remember, a ball at the bottom.
Did she? Yeah, maybe. I don't remember. I should look. I have the videos. I should look at what her motivation was. But it was mostly animated, so she could pretty much do anything. She bounced a lot. I remember that. Yeah. Yes?
Hi. I was wondering if there have been any developments in robots having manners, because I'm assuming we're going to have these robots, working with us side by side, unless everyone's remotely, present with robots all around.
There is some work on, I don't know if it's manners per se, but there's some work on legibility of the robots. So how can I know what especially if the robot's in autonomous mode, how do I know what it's thinking? So it turns out, like when we were doing navigation, we were using that tilt laser on the front of the robot to model the world, and a base laser, and not the sensors on the head. And so the robot would be like looking over here. Somebody would have programmed it, and the first navigation algorithms didn't bother to move the head. We're not using those sensors. We just leave it like this, and the robot's driving around like this, right? And it was really freaky. And we changed it, and we made it look where the robot was going. Just like put a little bit of code in to tell it where to look where you're going. And suddenly it was much more normal to be around. We've discovered that if you're driving a robot remotely, it's so one of the sort of fundamental things. You might not even think of it as manners, but who's driving this thing, right? It wasn't an affordance that we built into the robot. And so the robot's suddenly doing some weird thing, and it's like, well, is it run amok? Is it autonomous? Is somebody driving it? And whoever's driving it can see you, but you can't see them. And so we're coming to the point where we're saying, look, if you're going to do a remote presence system, like on the TechSci, the rule is you can't turn on the camera on the remote end unless your camera's on your end and there's a face on the screen. If you don't have a face both ways, it's a spy bot, and that's not really interesting. There's a lot of robots out there that are just cameras on wheels, but I don't want to be around those things, right? That's somebody spying on me. And so that's a level of manners. I think the autonomous manners haven't really been programmed in very much yet, at least in robots that I've seen, because there's not very many robots out there yet.
Sure. Well, I guess I was thinking about like manners in terms of body language and like proxemics, how close they're standing to you in your face, or
so we've actually done studies
like
of proxemics, right? So you do a study where you have you stand here, like I stand on this box, right? And now the robot comes up to me at some scary speed, and then stops at some distance, right? And you could walk up to me at your normal walking speed, a meter per second. And when you get up to a certain place, you're going to stop naturally. We can have the robot come and stop right in front of you, right? And we see when you jump back, right? So we've done a number of those studies to kind of understand what's comfortable, what's reasonable. And those things will go into the robots. But if your robots are being controlled by people, the politeness is up to the people, the manners are up to the people.
And, yeah, per culture, right?
Yeah, exactly right. It's indexed.
You can't, hold on.
Don't do that. I mean, so you could have an advisor for the remote person. What you're doing has the following unexpected properties, or not visible to you.
Yeah, there's actually some interesting ones. Like somebody was at dinner tonight. Somebody was talking about just regular teleconferencing, and somebody who had their, they were on a big screen and, kind of itching their nose and stuff, right? And if you're up there itching your nose, it's kind of weird, right? And you're not thinking that you're not watching yourself. There's a lot of those unexpected consequences. It turns out just if you're going to drive a remote presence device, how you light yourself matters, right? If you have a window behind you and it's bright outside, you don't look good on camera, and that means you have this box coming along with this bright glare. It's not the same experience as it would be because you're not lit the way you are in the remote room. So there's a lot of those kind of issues to deal with. Yes?
Well, I had one question. Now I have two based on the last one. So the one I was going to ask, I'll ask first and then the second, which will tie into the last question. So the first question is, there's a lot of robotics capabilities out there already. And so how are you, or you might have talked about this, how are you integrating with that? The second question I worked in Kaiser's Innovation Center, and one day we brought in this robot, and it kind of looked like your employee's one, but we ended up, I threw a doctor's lab coat on it because we were having it remote calls into the hospital room. And so in tagging with that, it seems like, are you guys working on some personifying, making it, because it just felt like too uncomfortable to have, this robot coming in and treating somebody.
Yeah, I mean, it's interesting. That's one of those things. I'll answer the second question first and get you to remind me of the first one. The question about what does it take for a robot to be acceptable in an environment is going to change over time. I found out recently that at remote hospitals, there's starting to be RoboDoc only at night, meaning that at nighttime, the only physician on staff is in the emergency room, and any other physician that's needed comes through one of these robots. And they become more acceptable as you get used to them. And once you explain to the patients that your choice is a resident who doesn't know much about what you have, or you can get a world expert from somewhere else in the world. It's the middle of the night, but it's daytime for them, and so you're getting actually a world-class person, who's educated at the Mayo Clinic. You're like, I'll take that doctor, right? And even if the robot's not wearing a lab coat, you're probably okay with that. And so as you get more experience and as you get introduced, people get more and more comfortable with these things, because it is, at the end of the day, just a doctor, and you really are just asking for their knowledge, not necessarily their skill, unless it's a surgeon, in which case you'd really like them to be local. What was the first question?
It was about integrating or working with other technologies, robot technologies are out there already?
Yeah, so there's, personal robots is kind of dependent on lots of other fields to integrate and make things work. So we get gear trains from the industrial robots sometimes. We get our sensors from the video game industry, right? We get computers from the computer industry. So we're putting together all these pieces. There's a lot of robotics technology out there. On the soft side, a lot of times that's open source. And what we've done is created ways to bring those open source packages together into one integrated framework so that everybody can use the best of breed. And so, yeah, when there is robotic technology, researchers always pull it in. And then when you're building a robotic product, you pull it in if you can afford to, if it's the right thing. Yeah. Okay. Thanks very much.